Now it is a good time to talk about the notorious topic, elliptic curve cryptography. So, in order to understand everything behind this elliptic curve cryptography, we require a lot of algebra, algebraic geometry, and so on. So, we don't have much time for that. So, we will briefly mention what the idea is about and why it is somewhat more secure than RSA. So, let's start with the definition, let's say, of elliptic curve cryptography. So elliptic curves are actually curves that are defined like this. So y squared equals to x cubed plus a times x plus b. So depending on these constants a and b, the figure of the elliptic curve becomes something like this. And it is so these actually drawings are from real numbers. So in the real plane, the elliptic curve looks like this. But if you draw it in the complex plane, you will see a torus with a hole in it. So since there's only one hole in elliptic curves, we are also calling them genus 1 curves. But it is beyond the scope of this talk. So you can think as that an elliptic curve is something like this. So if you define an elliptic curve in a finite field, so if you define it in real numbers, this a and b can be any real number, and x and y values can be any real number. But if you define it in finite fields, for instance, if you define it in a binary field like f2, where a and b can be 0 or 1, so you can see that the figures will be a little bit limited. But anyway, let's move on. So why do we talk about elliptic curves when we are talking about cryptography? We always said that the hardness of the discrete logarithm problem depends on the group that you are working on. So we said that if you work with the multiplicative group, it is somewhat secure, but if you work on the additive group, it is not secure, so we can easily break it. So the group actually affects the security of the discrete logarithm problem. So mathematicians thought about groups that are somewhat more secure than the multiplicative group. So elliptic curves are a good example for this. So if you define an addition operation on the points of an elliptic curve, this defines the algebraic group. So idea is as follows. In order to define an addition operation and in order to be a group, it needs to satisfy some properties. So for instance, it needs an identity element. Every element should have an inverse and so on and so forth. So let's see from these pictures how we define the addition operation on an elliptic curve. So assume that this is our elliptic curve and we have 2 points on this curve, P and Q. So addition operation is defined like this. So you want to add the point P to the Q. So what you do is draw the line that passes between P and Q. So there is only one line that can pass between two different points. So when you draw that line, due to the equation of the elliptic curve, it has to intersect the curve at the third point. So when you find that point, take the inverse of it with respect to the x coordinate. So just take the mirror of it, and we define it as P plus Q. So this is a very strange way of defining an addition operation. So at this point, it doesn't much related to the coordinates, but the line passing through these points. Then you take, so the y coordinates, you just multiply it with -1, and you got this point. So this is how you add 2 points on an elliptic curve. A question is, how can I add a point to itself? So if you know, for instance, P, how do you calculate 2P? Idea is as follows. So you have the point here. Just draw the tangent line that passes through that point. It has to intersect the curve at another point. Again, take the mirror with respect to the x-axis, and you get 2P here. So this way, you know, you can find MP, so you can add P to itself n times. So discrete logarithm problem will be about it actually. So when we were talking about G to the X in the multiplicative group, in this picture, it will become X times G because we will be adding the point G to itself X times. So in order to be a group, every element should have an inverse. So inverse is defined like this. You just multiply the y coordinate with a minus sign. And again, we need an identity element somehow, so natural element. So in this case, it is assumed that there is a point at infinity somewhere above. So this is why you adding that point to a point on the curve gives you the same point. For instance, in this case, assume that we have the point at infinity here. We denote it by this 0 here, so it is a point like this. So when you add p to that 0, you draw the line here. So it intersects the curve here. When you multiply it with minus sign, you get the p back. So this is why this element at which we call the point at infinity as the identity element. So that point at infinity might seem somewhat strange, but the mathematics works, let's say. And when you think about it in the complex plane, it makes more sense. But anyway, so just think about this operations. It defines a mathematical group. But now the question is how we can use it in cryptography. Since we are drawing these curves on the real plane, there are infinitely many points on this elliptic curve. But we need to work on finite data, so we have to somehow think about the points that are finite. So what we do is as follows. When you have an elliptic curve over real numbers, when you consider it over a field or group like say Z89 here, this means that you're only considering the points which has the coordinates in this set. So the only remaining points becomes this, okay? So you end up with finitely many elements, but still any addition of 2 points here will give you another point here and so on. So you reduce the infinitely many elements here to finitely many elements here. One question might be how many points you would get once you do this reduction. Actually, there is a very good algorithm to check this. So we know around how many points we get when we have an elliptic curve and reduce it over, define it over a finite field. So this is the basic idea actually. So this way, we can add 2 points and so on. So this way we can also define discrete logarithm problem on elliptic curves. Most of the time it is referred to as elliptic curve discrete logarithm problem. The good thing is that this problem is harder compared to the multiplicative group. The algorithms there we have to discrete logarithm problem does not apply here. For this reason, when you use elliptic curve cryptography, you can choose your key size smaller compared to other algorithms or other cryptographic algorithms that rely on the discrete logarithm problem, but on the multiplicative group, not the elliptic curve.